Hi, welcome to this video as we're about to see this biathlete taking shots at a target. Pretty good shots, but he was pretty close. It would have been more impressive if he was further away. And it would have truly been excellent shots if he was at an even larger distance. But moreover, shooting from such a big distance with such a low variance within the shots, they're all very closely together, tells us something else. It tells us that the shooter has a steady hand. He is robust, if you like, or insensitive to parameters such as sudden gusts of winds, snowflakes falling, or a loud audience cheering on the side. So the main topic of this talk is going to be parameter sensitivity patterns in the plant propagation algorithm. And it's a study done by Marleen DeJonge and myself, published at IJCCI 2020, and was nominated for the Best Student Paper Award, as Marleen DeJonge was still a bachelor student at the time of publication. So what is this plant propagation algorithm then? The plant propagation algorithm holds a number of potential solutions to some intractable problem in its memory and ranks these solutions from being very fit, if you like, being very good, to not so good. And then the top of the population generates offspring, generates a lot of offspring with only little mutations. Yes, and as we go down all the way to the bottom produces only very few offspring with many mutations. That's the complete inverse. Okay, so first there's some normalization done in the fitness, and then these formulas, they kind of guarantee that the inverse proportionality becomes a fact. Okay, so the top of the population produces many offspring with small mutations. The bottom of the population produces a few offspring with a lot of mutations. It's an algorithm devised by Abdelha Salhi and Eric Fraga, both from the UK, in 2009. It says here, but I think it was in 2000. Okay. Like all evolutionary algorithms, the performance might depend on the specific parameters of the algorithm. Yes? And in this case, the two most important parameters are the size of the population. Are you going to keep 10 individuals in the population, or 50 or 100? Makes a lot of difference. And the maximum number of offspring. Of course, it's tempting to put it as high as possible, but for a fair comparison, we'll use function evaluations in a moment. But let's have a look at the problems first. So this is what we call a set of benchmark functions. And these benchmark functions have very clear mathematical descriptions and kind of emulate a fitness landscape, if you like. These are all two-dimensional, as they have two parameters right here and a fitness or an error value on the vertical axis. But they can be deployed in 5, 10, 20, 50, or 100 dimensions. You can see here by these little d's and these sigmas, which also accompany the domain. Now, these benchmark functions are extracted from a combination of studies, and we did that purposely to make our results comparable to other studies. They have a lot of different properties, such as being multimodal, or being convex, or having valley-shaped global minima. But what we took care of is that all the local minima, as this is a minimization problem, it's finding the lowest value, the lowest cost value, if you like, putting it at 0. Now, many of these already have their global minimum at 0, but the Schwefel function had to be translated. So 0 is the ultimate target in these fitness landscapes for the plant propagation algorithm. So what we did in the experiment of determining the parameter sensitivity is we took 400 parameter configurations for the planned propagation algorithm on each benchmark on 6 different dimensionalities. Not only on 2 dimensions, also on 5, 10, 20, 50, and 100 dimensions. So for each of these instances of benchmark functions, we used 400 parameter configurations, we varied the population size, and we varied the number of maximum offspring. Then, for each of those settings, we ran 10,000 function evaluation runs. And you have to keep this constant, because otherwise you will just have a lot of solutions in your population which produce a lot of offspring, and that makes the comparison unfair. So stick to the same number of evaluations for each run, right? And it does give you a lot of data, but that's only good for your results. So let's have a look at some of these results. So this is 6 heat maps for one benchmark function on 6-dimensional instances. Rosenberg function on 2 dimensions, which you can see here, 5, on 10, on 20, on 50, and on 100 dimensions. And these heat maps over here, they show you the attained value, so how close it came to the ultimate bullseye of 0 for various settings of maximum offspring and population size. And the first thing that you can see is that these heat maps have very low variance in between. So that indicates that it really doesn't matter what kind of parameters you choose for any of these singular benchmark function instances, right? A population size of 35 with a maximum number of offspring of 10 does just as well as a population size of 10 and a maximum number of offspring of 2 on 2 dimensions for the Rosenberg function. But you can also see that between these heat maps, there is a lot of difference, as the final error after 10,000 function evaluations becomes higher as the number of dimensions gets higher. Now, this is somewhat understandable because the dimensionality in this function is always summed up, if you like. Those big sigmas you saw in the beginning, it kind of adds to the error. So we also try to make a comparison between those dimensionalities. And for that, we did the following. So the planned propagation algorithm, as most evolutionary algorithms, start off with random solutions. And here in this blue hump, you can see the random solutions of 10,000 initial values. And then after it starts running, it starts doing its magic, it starts approaching 0, it starts going towards the bullseye. The minimum and the maximum parameter settings, so this is the best parameter setting and this is the worst performing parameter setting, form a relatively tight space. Same goes for 50 dimensions. This is 10 dimensions, this is 50 dimensions. But for 10 dimensions, you start off closer to the bullseye because of this sigma than for 50 dimensions. So how should we compare them? And this is where we go back to our biathlete, who at a larger distance still has the same distance between the shots, is a better performance, right? So what we did is we divided this distance by this distance. So if this is further away to the right, the performance gets better or less parameter sensitive, if you like. So what does this division parameter sensitivity look like for all the functions in all the dimensions? Here we can see it. On the horizontal axis, there's the number of dimensions. Remember, we didn't do all of them because we already have a lot of data. We just did 2, 5, 10, 20, 50, and 100. And this escalates all the way upwards. It's the same here. It's the same here. It's the same here. Yes. And the error on the vertical axis is a little bit different, but we're just looking at the kind of gross pattern, if you like. And we see a couple of different regimes, 3 to be precise. The tablet and the ellipse function, which are here, can be bound on the top by a straight line. So they are increasingly sensitive to parameter settings, but ever less so. It doesn't increase really fast. It increases sublinearly. Cigar, sphere, Rosenberg, and DeJonge, they can probably not be bounded by a line from the top, so they increase faster than linear. They might increase superlinear. Polynomial, exponential, we don't know. At least that's what it looks like. And then we have this third very interesting pattern in which it first increases a lot, the sensitivity to parameters increases a lot, but then drops down very rapidly, right? And this might have something to do with the formulation of the benchmark functions themselves. Might, we're not sure. Because if we look at these up-down phase transitions for Rastergen, Schwefel, and Ackley, we see that they have these trigonometry functions in there, right? And if we look at these sub and superlinear parameter sensitivity regimes, we see that it's all, if you like, simple quadratics. And the only exception here is the DeJonge function, who is in the superlinear regime, but does have a trigonomic function in there, a cosine, which actually somewhat belongs to the up-down phase transition functions. But if we look very, very closely, we can see, with a little bit of fantasy, I must be honest about that, we can see a little bit of up-down phase transition here, starting in the beginning. And it's very interesting to see that this up-down phase transition is always somewhere between 5 and 10 dimensions. So some of these functions with trigonometry in there are hardest to parameterize for the planned propagation algorithm, between 5 and 10 dimensions. And after that, they become easy. So that's all for me now. If you have some comments, please drop them and drop your questions also, and I'll be happy to discuss them. And otherwise, thank you for watching and see you again sometime. Bye-bye.